This video is part 2 of a series where we examine simple linear regression within StatCrunch. In this video we're going to discuss several key statistics which are given in the usual regression output. We'll use the same variables as in the previous videos, distance to and commute to, from the early fall 09 class survey. Now it's going to be important to remember that commute to is given in the dataset in minutes and distance to is given in miles. Now, here's our usual regression output. You'll remember that we used StatCrunch to create this output in our previous video. The first statistic we'll examine is called the coefficient of determination, but it's more generally known as R squared. Now we usually give the model R square rounded to 2 or 3 decimal places, so we see that the R square for this model is 0.207. The model R square is a measure of the overall fit of the model. That is, it tells us how well this model fits our data. R square is always a number between 0 and 1, and it's interpreted as the proportion or percentage of the total variation in the y variable that's explained by the regression model. Again, that's the proportion or percentage of the total variation in the y variable that's explained by the regression model. So we'd interpret this R square of 0.207 by saying that 20.7% of the variation in commute time, that's the y variable, is explained by the regression on distance traveled. And we can also take this to mean that about 79.3% of the variation in commute time is explained by other factors. What are those other factors? They could be things like, does the student drive to school or ride the bus? Does the student drive primarily on city streets or take the interstate, etc.? Now let's point out one more fact about R square. We've referred to this regression model as a simple linear regression model, and that's because there's only one x variable, distance traveled in this case. Now, when we calculate the model R square for a simple linear regression model, it turns out to be the square of the Pearson linear correlation coefficient R that we calculated in an earlier video. So that is right here. Now we can check this by taking our correlation coefficient of 0.455 and squaring it. And we're going to see that our result will round to 0.207, our value for the model R square. But it's important to remember that this relationship between the correlation coefficient and the model R square only holds in the case of a simple linear regression. In other words, in a more complicated regression model, this result won't hold. So, now that we know something about the overall fit of the model, let's look more closely at the regression coefficients. First, we'll take the y-intercept term. That's 13.44 in our model. This means that our model estimates a value of 13.44 for y if x were equal to 0. Now when we're thinking about interpreting the meaning of the y-intercept term, we have to ask ourselves if it makes sense for our x term to be 0. Since our x term in this model is distance traveled from home to the college, it probably doesn't make sense to think about a student who travels 0 miles to school. So when thinking about interpreting the y-intercept term, you have to remember that the y-intercept is going to give us the predicted value of y when x is 0. And so we have to think about whether or not it makes sense in the context of our modeling problem to treat 0 as a reasonable value for x. And then even if it does make sense, we also need to check to see if we have observations in our data near x equals 0. If not, then giving an interpretation to the y-intercept would amount to extrapolating outside the scope of our original data. Never a good idea. And so finally, we'll consider the slope coefficient, equal to 0.89 in our model. The slope indicates the average change predicted in the y variable for a 1 unit change in the x variable. So in our model, we can say that for each 1 mile increase in distance traveled, remember that's the x variable, for each 1 mile increase in distance traveled, the average commute time is predicted to increase by 0.89 minutes. So one more time. For each 1 mile increase in distance traveled, the average commute time is predicted to increase by 0.89 minutes. And by the way, these regression coefficients are sometimes referred to as parameter estimates. They're given again right here in our output. Here's the estimate for the intercept term. Here's the estimate for the slope. And these are sometimes referred to as parameter estimates to emphasize that they're only the estimates for the true population parameter values in the model. If we collected a new set of data and used it to create a new regression model, then no doubt our regression coefficients would change a bit. Now, in our next video, we'll use our regression model for prediction, predicting new values for the y variable given some particular values for x.